Let's start.
Yes. So, good evening, everyone. So, let's recap back to what we discussed in the previous session. So, myself, Praveen, and welcome you to IGC's previous year GATE solving sessions. So, today we will be focusing on GATE 2012. This is the first year in which they ask questions from NAT, the numerical analysis type. So, the NAT was first introduced in this year. So this year had the most number of performance questions. Most number of questions from performance. Basically, the flight mechanics part. Okay, so let's get started. So we in 2012 they asked 7 1-mark questions and 7 2-mark questions. So giving a total of 21 marks. So this is the maximum number of questions that they asked. 14 questions, which is huge. Considering that out of 65 questions, 14 questions were reserved for flight mechanics. So that much important is this subject. Okay, right. So let's get started with the first question. An aircraft in trimmed condition has zero pitching moment at. We have four options: its aerodynamic center, its center of gravity, 25% of its mean aerodynamic chord, 50% of its wing root chord. So let's try to see this. So let's underline this keyword trimmed condition, right? Let's look at what does this trimmed condition mean. So trimmed condition is a condition at which your moments are zero. So which means if the moments are zero, moment coefficients are also zero about the CG. Okay, because you are taking net moment about reference point. In our analysis, it was the CG that we defined, about which we determine the moments acting on the aircraft. Right? So which means it has zero pitching moment, has about its center of gravity. Okay, so this has to be the answer. So hope you guys don't have any doubts in this. So this is CMCG is equal to zero. Okay, so this is the first answer. If it is zero about its aerodynamic center, that is a different thing. Okay, so let's look at the next question. So if you don't have any doubts, in an aircraft, constant roll rate can be produced using ailerons by applying. So we have four options again: a step input, a ramp input, a sinusoidal input, and impulse input. So again, let's look at this very simple one. For this, it's pretty simple. So when you have a step input, what happens is step means you're holding, right? So it's like this thing. You're holding at a constant fixed value, right? So which means we're holding the ailerons at an angle, which means which will create what? Continuous roll, right? That is, let's say, you have an aircraft like this. Let's say we are now giving deflection like this. What will happen? If you fix it like this, basically, the aircraft will go up. Basically, by fixing this angle, lift on this will increase, lift on this will decrease, and this will go on and on. Thereby, basically spinning about the x-axis, right? So which means what you achieve a constant roll rate. Now that's what is asking a constant roll rate, and that is achieved by using a step input. Hope you guys don't have any doubts in this. Okay. So if no doubts, let me go to the next question. The critical Mach number of an airfoil is attained when the free stream Mach number is sonic, the free stream Mach number is supersonic, the Mach number somewhere on the airfoil is unity, the Mach number everywhere on the airfoil is supersonic. Okay. So again, this is a pretty simple one. Let's do this. So first, you have to understand what is this critical Mach number. Okay. So let's rewind back. Let's say this is an airfoil. Let's say a free stream coming in. Let's have 0.5, something like that. And over this, what happens? Over the upper surface, flow gets accelerated, right? Which means a streamline will get curved like this, and a streamline would be like this. Yeah, the curvature effect is large, so which means what? There is a net pressure gradient acting in this direction, thereby constituting a lift, right? Basically, correct. So which means so there is an acceleration in this region. Okay. Now, if you increase, let's say this Mach number is free stream 0.5. So in this region, your Mach number can reach to 0.6, something like that. Let's say you accelerate it to 0.6. Now in this case, it might reach to your let's say it reaches some m is equal to 0.8. Let's say at some value 0.7. Let's say Mach number becomes sonic on the top surface of the Earth. As this and the local Mach number over the airfoil has reached sonic condition, right? So that Mach number, that the Mach number at which we had attained this sonic Mach number locally over the airfoil is this critical Mach number. Okay, so which means it is not compulsory that flow field over the entire airfoil has to be supersonic, but somewhere over the airfoil, the flow field, the flow conditions have reached sonic conditions, right? So, which means if I go back to my answer, so the Mach number somewhere on the airfoil is unity. Okay, so this is the definition of critical Mach number. Okay. Hope you guys don't have any doubts, and please, feel free to ask any questions in the chat box. And that motivates me. And if you like the session, please put a thumbs up. That help motivates us to do more and more sessions like this. Okay. Right. So if no doubts, then let's go to the next question. During the ground roll maneuver of an aircraft, the forces acting on it parallel to the direction of motion. We have four options: is thrust alone, is drag alone, or both thrust and drag, or thrust, drag, and a part of both weight and lift. Pretty simple one. Let's do this. During the ground roll, which means, if I write down the equation, so let's draw an aircraft basically first. So which means we have a thrust in this direction, drag in this direction, and so this is my normal. Let's say a surface is like this surface friction. This friction force is, let's say, friction Ff. This is basically mu times your W, and which means you'll have a component of lift minus drag in here. So if I do a force balance, this will be T minus mu times W minus L, where mu is your the surface roughness or the coefficient of friction of the surface. Right? So which means the horizontal surface is basically horizontal surface summing up. So it depends basically on the thrust, drag, and both lift and weight. Okay, so which means if I go back, so the forces acting on it parallel direction of motion are thrust, drag, and a part of both weight and lift. Okay, so this has to be the answer. I hope you guys don't have any doubts in this, right? Okay, right. So let me go again. Let me go back to the first question. So yeah, so this is the first question. An aircraft in trimmed condition has zero pitching moment at dash. Okay, so basically, so a trimmed condition is one, in which your summation of moments are zero. So if moment is zero, which means that the coefficient of moment has to be zero, and about which point, about the CG, right? So which means that the CMCG is zero. So which means if I go back to the options, so this has to be the correct one. It's center of gravity. Okay, so this is the first one. Okay, hope you understood, Mukund. And if I go back to the next question, so in an aircraft, constant roll rate can be produced using ailerons by applying. See, so when I deflect an aileron, let's see, fix it like this. What will happen? Here you will have loss of lift. Here you'll have gain of lift, and here you'll have loss of lift. So which means aircraft will at some time it will attain a state like this. Sorry. After some time it will attain a state like this. I'm drawing it in the wrong sense. It's just yeah. After some time your aircraft will be like this, and after some time your aircraft will again come back like this. Right. Now this is your right wing and this is left. So this rolling is constant and it happens like that, right? So which means uh, if you want to have a constant roll rate, you need to have a step input, right? Whereas if you want to have a variable roll rate, that is constant roll acceleration, in that case you can have a ramp input or an impulse input or sinusoidal input. Okay. So for a constant roll rate, you need to have a step in basically fixing the angle such that your rotation is continuous. Right? So that is basically, let's say, it takes around, let's say, 5 seconds to go from here and come back to here, right? 5 seconds, right? 5 seconds, so 360 degree, right? So 360 by 5 seconds is what, 72 degrees per second, right? So let's assume that case. So this is the constant roll rate that I was talking about. Okay. So this is maintained by using a step input, right? Okay. Let me go to the next question. So this is what I explained. A critical Mach number. This Mach number somewhere on their file is Unity. So for more details, please refer JDA book. Fundamentals of Aerodynamics by John D. Anderson. Please refer to this book. It is helpful. Right? Okay. Let's go to the next question. This is also done. And I hope you don't have any doubts in this. So thrust, drag, and no weight minus lift. Right? Okay. So having said that, let's do this problem. An aircraft in a steady climb suddenly experiences a 10% drop in thrust. After a new equilibrium is reached at the same speed, the new rate of climb is. We have four options: lower by exactly 10%, lower by more than 10%, lower by less than 10%, and unpredictable quantity. Okay, so let's do this. So, what is asked? Suddenly experiences 10% drop in thrust. Okay, so there is a drop in thrust. Let's keep that as such. And new rate of climb. So which means let's write on the rate of climb formula. So what is the rate of climb? So this is my rate of climb, which is equal to V sine the climb angle, which kept it as gamma. So that is basically equal to what? It is T minus D by W times your V. Okay. Think yeah, this is the case. Okay. Now let's assume that let's fix some numbers. Initially the T is 100 Newton. And let's say the drag is 50 Newton. Okay. So now he says that because of the drop in thrust, the new thrust, let's say T dash is 19 Newton. There's a 10% drop in thrust, right? If I go back to this question, 10% drop. Okay, so which means the new thrust will be 19 Newton, right? Now, my original rate of climb is what? That is basically 100 minus 50 by W into V, right? So which is basically 50 by W. Now, what happens to my new rate of climb, modified one? That is equal to 90 minus 50, which is 40 V by W. Okay, so which means what is the percentage change of ROC? So it is basically what minus 20%, right? There is a 20% decrease, right? So which means I can just simply say that the answer is B, lower by more than 10%. Okay. Hope you guys understood this. Right? Any doubts? I hope you don't have any doubts. If no doubts, then let me go ahead basically. Again, let me just repeat what I said over here. So it is a steady rate of climb. So this is what is the ROC is. It is T minus D by W. And I have because we can't solve directly like this. So let's give in some values so as to ease our simplification. And T, let's fix it as 100 Newton. And D, let's fix it as 15 Newton. And now the new thrust is basically 19 Newton. And because of which the original rate of climb is 50 V by W, new rate of climb is 40 V by W. So there is a percentage decrease which is basically 20%. Hope you guys understood. Right. Let's go to the next question if no doubts. Again, I'm saying the chat box is open, so you can just type in any questions until the live session is going on. Okay. Right. Take this problem. In an aircraft, the diving maneuver can be initiated by. So we have four options: reducing the engine thrust alone, reducing the angle of attack alone, generating a nose down pitch rate, increasing the engine thrust alone. So you have to understand what is the dive maneuver. So dive is basically, let's imagine you are diving in a swimming pool, so which means you are falling down, right, with your head down. So which is for an aircraft, diving basically means your nose has to be down. And how do you do that? Let's say an aircraft is flying at a straight and level flight. How to do that? By generating a nose down pitching moment, correct? So and how do you do that basically? It is by generating a nose down pitching rate, which is the options here. If you generate no sub pitch moment, what happens is aircraft will climb. You can write that down as well. Put it as a note. If we generate a nose up pitching moment, aircraft will climb. Okay, this is what you have to remember. Right? Hope you guys don't have any doubts. Then let me go to the next problem. In an aircraft, elevator control effectiveness determines turn radius, rate of climb, forwardmost location of the center of gravity, aftmost location of the center of gravity. So let's try to do this again. Very simple one. So the elevator control effectiveness, that is basically your CL delta E. So if I write it in here, is equal to st by s eta t cl alpha t into tau, where your eta t is the ratio of the dynamic pressure at the tail by dynamic pressure at the wing, which is given by half rho v square at the tail by half rho v square at the wing, and your tau is d alpha t by d delta e. Okay, back of the tail with respect to the elevator deflection. Okay. Right. So, so in theory, this elevator control effectiveness, it basically dictates, the forwardmost location of the center of gravity. Okay. So if you refer to theory in R.C. Nelson or in Parkinson Hedge, there is a big derivation that precedes this, and once the derivation is done, you will come to the conclusion that this term has there's a dependence of this xcg bar, which we discussed in the last session. So hence we can just say that this elevator control effectiveness basically determines the forwardmost location of the center of gravity. Okay. So again, because I can't do the whole derivation because of time constraints, I'll give you the lead. So kindly refer and do any of these things or do all three of them. That will be better. AK Ghosh NPTEL lectures. You can also do, like I said, RC Nelson book. I think some stability and automatic control. Just search it in Google. And another thing is Parkinson Hedge. Refer these refer these two books and this lecture. That will help you, to go through this derivation, right? Uh, so if not else, let me go ahead. Okay. Right. So take this question. An aircraft has a steady rate of climb of 300 meter per second at sea level and 150 meter per second at 2500-meter altitude. The time taken in seconds for this aircraft to climb from 500-meter altitude to 3000-meter altitude is dashed. So it's underlined certain the data that is given. Steady rate of climb of 300 meter per second at sea level and 150 meter per second. Which is what rate of climb at 2500 meter altitude. The time taken to climb from 500 meter to 3000 meter. Okay. Again, it's a simple one. Let's do this. So which means what? So at a height of, you can just write it down. So at a height of 0 meter, my rate of climb is what? 300 meter per second, right? And at a height of 2500-meter altitude, my rate of climb is what? 150 meter per second. Okay. So which means I can construct because we have 2 points, so basically we can construct a line, which is basically 2 point form. If you are given 2 points, x1 comma y1, x2 comma y2, you can basically construct an equation using this form, right? If you remember, y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1. So if I do that, so I will simply get it as y will be equal to 300 minus 0.06x. Okay. So let's bracket this up. This is the equation that we want. That this y is my rate of climb. Okay. Mind you, which is equal to dy by dt. Now, how will I get the time? So time is basically let me use same notation in here. Let's use okay. We rub this x off. Okay. I have to follow unison notation. So let's say y dash. This is y. Okay. Now if I integrate this, let me go to the next slide. So I have to integrate. So let me rewrite that. So dy by dt is simply 300 minus 0.06 h. So 0.06 y. So which means what? Dt is equal to dy by 300 minus 0.06 y. Okay. Hope you guys understood how we got this, right? Pretty simple, isn't it? So if you integrate this, what is he asking is from 500 to 3000 meter. You will get the answer as close to 13.516 seconds. Okay, this will be the answer. Hope you guys don't have any doubts in this. Let me again explain what we did it in here. So you can just plot a line like this. At height equal, let's say this is the height and this is the ROC. At height equal to this 0, my ROC is 300. At height equal to 2500, my ROC is this. If you plot a line, you will get the equation of this line, right? By using the 2-point formula, right? And once you get that, you can just simply integrate it. What is my rate of climb? Rate of climb is basically dh by dt, right? So if I want to determine the time, it will be simply dh by ROC, correct? So that's what we are doing over here, right? So again, this is all that requires is simple manipulation. You see, it's not you don't have to use any fancy formulas in here. All it requires is the ability to comprehend problems and apply logical intuition. Okay, right. So if no doubts, then let me go to the next question. An airfoil generates a lift of 80 Newton when operating in a free stream flow of 60 meter per second. If the ambient pressure and temperature are 100 kilopascal and 290 Kelvin respectively, where the specific gas constant is 287 joule per kg Kelvin, the circulation on the airfoil is dash. Pretty simple. It's again a direct substitution formula. Let's write on the given data. What is given as lift is 80 Newton. Your free stream velocity is given as 60 meter per second. And your pressure is given as 100 kPa. And your temperature is given as 290 Kelvin. Okay. Circulation on the airfoil is in meter square per second. So if you recall from the Kutta-Chukowski theorem, I know that the lift is basically the product of density, velocity times the circulation. So which means he's asking circulation, but rho is also unknown. So first let's determine the rho. How will you use rho from ideal gas? Okay, this is basically P by R T. This comes from the ideal gas equation. Yes. So which means if I substitute back the values, so then simply rho will become P is what 100. This is 100 kilopascal is 10 power 5 by 287 times 290. You will get it around 1.201 kg per meter cube. So always while take decimals up to the third place, so that you won't miss out on the accurate values. Okay. So which means what will be my circulation? It is L by rho v. Substitute the values. So it is basically 80 by 1.201 times it's 60, right? If you simplify this, you will get it around 1.109 meter square per second. So bracket this again. So this is my required circulation. So please be careful with the virtual calculator and gate exams. Many people tend to make mistakes there. Okay, that's why. Okay, guys, understood? Any doubts in this? Please, chat box is open to put your questions. And if you like the session, please put a thumbs up so that helps us, more to do more sessions like this. Right. Let me go on to the next question. If an aircraft takes off with 10% less fuel in comparison to its standard configuration, its range is lower by exactly 10%, lower by more than 10%, lower by less than 10%, an unpredictable quantity. So let's do this pretty simple. Let's consider a piston engine aircraft. Okay, right. So let's. What is the range formula? Eta P by C, CL by CD, ln of W naught by W1. Okay. What is he saying is, so initially, let's assume that the W naught. Okay, you can just write it down. Let's assume W naught is 200 Newton and W1 is 100 Newton. So which means what the weight of the fuel is 100 Newton, correct? So if you calculate the range, let's use R1 in here. So this will be all these are constants. So it's, just keep it represent it as a Z, okay? Where Z equal to eta P by C, CL by CD. Z times ln of W naught by W1. That will simply become Z ln of 2. Okay, so this is the first one. Now in the second case, what is he saying is, if the aircraft takes off with 10% less fuel, right? So which means what? Your fuel is reduced, right? So which means I will have Z times ln of W naught by W1 prime. That will become Z ln of 1 point. Okay. Because like I said, if fuel is reduced, let's say 10%. Now fuel is 90, right? And what will be my W1? W1 is simply 110, right? And if you divide 200 by 110, you will get 1.9. Okay, that's what we are doing it over here, right? Oh, because understood how we got this 1.9, right? So what is the percentage change in R? The percentage change in R. So that is basically R2 minus R1 by R1. You can do that, and you'll get it around minus 7.4 percentage into if you do 100. Okay, so which means there is a change of 7%. Okay, even if you do it for a jet engine, let me come back to that. So answer has to be lower by less than 10%. Okay. So this is the answer. Okay. So I'll give you food for thought. Okay. You try this one with a jet engine. Okay. So do the same analysis with a jet engine where the formula is 1 by C, CL power 1 by 2 by CD. I think you'll have 2 by C. 2 by C, CL power 1 by 2 by CD. Root of 2 by rho s times root W naught minus root W1. So do this, and you see what is the change in range. Okay? You'll obviously get the same answer as well. Okay, try this out on your own. Okay, this is a food for thought for you. Yes, can I go on if no doubts? Okay, an aircraft is trimmed straight and level at a true airspeed of 100 meter per second at standard sea level. Further, a pull of 5 Newton holds the speed of 90 meters per second without retrimming at steady state level, standard sea level. To fly at 3000 meter altitude, where the air density is 0.91 kg per meter cube and 120 meter per second true airspeed without retrimming, the aircraft needs. So there are given four options: 1.95 Newton upward force, 1.95 Newton downward force, 1.85 Newton upward force, and 1.75 Newton downward force. So it's underlined certain keywords. So a true airspeed of 100 Newton per meter per second is given at a standard sea level. Okay, that's first thing. So further, a pull of 5 Newton holds the speed at 90 meter per second without retrimming. Okay, to fly at 3000 meter altitude, how much upward force is needed? Okay, and that too at 120 meter per second, true airspeed, right? So let's do that. Pretty simple problem again. So we know that what is the lift? It is basically given by this expression half rho v square SCL, where rho is the density, v is the velocity of the aircraft, s is the platform area of the wing, and CL is the lift coefficient, right? So in here, what parameters change as given in the question? It is rho and v, right? S and CL remains the same because they are not trimming it. Okay, it's again flying. So which means what? Let's treat that half SCL as some constant. Let's keep it as A. Okay. So which means what I can write L as A times rho V square. First determine the A value. A is simply is everything given in here? No, right? Okay. So 100 meter per second. Yeah, nothing is given. So let's keep that A as such. Okay. A is half SCL. So first determine this. L is equal to it is without any upward force. Okay, so it's basically your A times rho V square. This is without upward pull. Okay. Now in the second case, he's saying that you have a pull of 5 Newton. Okay. So that will basically become what? You will have to add a 5 in here. Plus you'll have a rho V square. That to mind you, this velocity is at 90. Okay. Whereas this velocity is at 100. So please, I'm just using notation so that you don't get confused with this. Okay. Next, other cases, the lift is with some upward force x plus again your A remains constant and density is at 3000 meter altitude and the velocity is 120. Okay. So the given data which is asked is this x. Okay. So we need to determine this x. So how will you determine the x? Just equate them. Okay. So which means I'll have this A rho V 100 square can be written as x plus a rho 3000 times v at 120 square, right? So if we solve this, so we get x as minus 1.95 Newton. So if you have minus sign, so which means what the convention is a negative direction, okay? So which means what? It's a downward force. Or you can just write as downward direction. So which means if I go back to my option, it has to be a 1.95 Newton downward force. Okay. Hope you guys don't have any doubts in this, right? Pretty simple problem, isn't it? Right? So please rework this problem again. That will help you understand this. Okay. Right? Okay. So if no questions, let me go ahead. So these are the last two questions for today's session. So we have common data linked questions. A wing and a tail are geometrically similar, while tail area is one third of the wing area, and distance between the two aerodynamic centers is equal to wing semispan, which is b by 2. In addition, the following data is applicable. Epsilon alpha is 0.3, epsilon alpha d epsilon by d alpha. CL is 1, CL alpha is 0.08 per degree, C bar is 2.5 meter, B is 30 meter, CMAC is 0, eta T is 1. The symbols have their usual aerodynamic interpretation. The maximum distance that the center of gravity can be behind aerodynamic center without destabilizing the wing tail configuration is dash. So we have four options: zero point 0.4 meter, 1.4 meter, 2.4 meter, and 3.4 meter. Okay. So let's underline certain keywords. A wing and a tail are geometrically similar. Okay. While the tail area is one third of the wing area. Okay. So let me write these down first. Because they are geometrically similar. Right? Because of geometric similarity. So my AT lift curve slope of the tail has to be equal to AW. and he has given STS 1 by 3 of SW, if I'm correct, okay? Because the tail area is one third of the wing area, okay? Right. So, what is the formula again? So, we know that XNP bar minus XCG bar is equal to eta T VH bar AT by AW times 1 minus dou epsilon by dou alpha, where my VH bar is, ST LT by SC, and your eta T is Q dynamic pressure at the tail by dynamic pressure at the wing. Okay, everything else is given. Okay, so this is 180 by AW is 1. Substitute all the values. So X NP bar minus XCG bar is equal to. So eta T is it given in the question? 1. Okay, so you can take it as 1. Substitute it as 1. VH bar is for STLT. So it's basically 1 by 3 times, LT by C bar. If you simplify that, you will get as 2 times 2 times AT by AW is again 1, and times 1 minus dou epsilon by dou alpha. What is epsilon alpha? Epsilon alpha is dou epsilon by dou alpha. That is given as 0.3. Okay. So 1 minus 0.3. So this will give you 0.7 into 2, which is 1.4. Hence the answer is 1.4 meter. Understood, guys? It's pretty simple again. Okay. Again, what I'm saying is, if you're not able to do this, just revisit your formulas again. Like I said, all the problems are like this one. Just work out the problems and rework your theory, and then problems are very easy to solve. Okay, right. So last question for today's session. Take this problem again, same question, but this is a linked one. So I have the data is known to you. He's asking the angle of incidence of tail to trim the wing tail combination for a 5% static margin is dash. So we have four options: minus 1.4, minus 0.4, zero point 0.4, and 1.4. Okay, right. Let's do this again. Simple problem. So first, let's write down the AT. AT is equal to AW, which is 0.08 per degree, right? Which is given in the question, right? And what else is given? The angle of incidence of tail to trim the wing tail combination for 5% static margin. Okay, so let's write down the static margin as 5%. Okay, we'll come back to that. And the CL is 1, right? So which means what? CL wing. Okay, so therefore I can write the alpha wing as, it is basically, you are divided 1 by 0.08, so you'll get it as 12.5 degree CL by AW. Okay. This is the angle of attack. Okay, let's keep it aside. Now, what is my XCG minus XAC? We use the formula substitution of the wing. This is simply 1.35. And what is my XCG minus XAC of the tail? It is basically, I can write this as AT. I have to convert this into per radians. Okay, so we'll have 180 by pi plus I will have a 0.05. Which means what? If I use this for again, so don't be hardened with so many formulas. Again, these formulas appear everywhere, so it's very easy to use formulas like this. Okay, unless your theory is strong, you can't solve these problems. That's my word for you. Okay, so best way to do these problems is to learn the theory first and then approach the problem. Okay, so which means I can write in this way as XCG minus XAC times CL at the tail is equal to XCG minus XAC at the wing times CL wing. So from this I can get the CL at the tail as 0.29. Okay, because I have all the values in here. Okay, simplify this, you'll get some value. Substituted that in here, you will get a value. Okay. Now, what is my CL tail? I can write it in this way as it is basically AT times alpha T times ST by SW. Okay. So, this is basically what AT is given, which is 0.08 per degree times alpha T is alpha times 1 minus epsilon alpha plus I. This I is to be determined times ST by SW. So solving for I, substitute all the values in here, you will get the I as minus 1.4 degrees. Right? Hope you guys understood this. Okay, guys. So what I would suggest is to rework this problem once or twice until you get a feel of it. Okay. And once this is done, again, problems like these you can solve it on your own, without any external help. Okay. Right. So I think with this is our last problem for today's session, and thank you for attending this session. And hope your doubts are clarified, and rewatch this video if you have any doubts, and please subscribe to our channel and watch our videos so that helps in your gate preparation. Okay. Okay, guys. See if no doubts, let's wrap up today's session. And thank you once again. And see you. Have a good day. Bye bye.